Good morning. Last class we discussed about the molecular weight and its distribution of polymers, and I showed that an order of weight average molecular weight greater than viscosity average molecular weight greater than number average molecular weight, which shows a polydispersity in a polymer sample, and the ratio of the two MW bar over Mn bar gives the polydispersity index, and values of polydispersity index beyond 1 indicates a broad distribution. Depending on the polydispersity value, one can select a suitable polymer sample or sample for production of different goods. Now, there are various techniques, as I mentioned, for measuring the molecular weights or determination of molecular weights. Now, here is a table which shows the different techniques like light scattering, membrane osmometry, vapor phase osmometry, electron and X-ray microscopy, isophiastic method, that means isothermal distillation, ebullientiometry, boiling point inhibition, cryoscopy, freezing point depression. So, and the range of molecular weights which are sensitive to each of these different molecular weight techniques are shown over here. So, from this you can select. So, for very high molecular weight, say ebullientiometry cannot be suitable, whereas for low molecular weight membrane osmometry cannot be suitable. Others are also end group analysis. End group analysis, I means there may be some polymer samples, polymer molecules whose end groups contain certain functional groups. Say in case of condensation chain polymers, there may be functional groups like amine, halogens, carboxyl group, hydroxyl groups. So, those end groups could be analyzed, and by analyzing the end groups one can calculate the molecular weight. Details of end group analysis can be available in the book of Professor P. Ghosh. In case of addition chain polymers, end group analysis methods can also be applicable provided initiators are functionalized. So, initiator fragment remains attached to the end of a polymer chain. So, by counting the end group, one can calculate the molecular weight by end group analysis. So, this way various other techniques are also available. This is for your information only. If you need in future for determination of molecular weight, you can go with any of these techniques. And chromatography is a very good technique for molecular weight determination. Although it is a secondary method, it needs a calibration standard based on which you can get the distribution curve. From that distribution curve you can get the molecular weight also. What is chromatography? Now, there is a technique known as gel permeation chromatography. You know what is chromatography? Chromatography is a separation technique from a mixture. If there are more than one components in a mixture, those components can be separated by chromatography. There are various techniques in chromatography: thin layer chromatography, column chromatography, high pressure liquid chromatography. So, TLC, column chromatography, gas chromatography, high pressure liquid chromatography, and GPC. GPC is gel permeation chromatography. Basically, in all these techniques, a stationary phase is used, which is highly active. That stationary phase, when comes in contact with the mobile phase containing the components in a mixture to be separated, then there some interaction occurs between the stationary phase and the components in the mobile phase, and those components in the mobile phase which are to be separated gets absorbed or interacted or held by the stationary phase. This way a separation can be affected. If you think of column chromatography is a very simple technique. You have to take a long column, vertical column, which should be packed by a stationary bed, say Sephardex, which are something say silica or alumina particles, or I do not know exactly say the composition of Sephardex, but it contains some stationary phase. So, that stationary phase is used for packing the column with the help of water, which is used as mobile phase there, or sometimes organic water mixture can also be used. After packing, then this from the top of the column a small quantity of solution is added, poured onto it, then gradually continuously some solvent, that may be a mixture of 1 or 2 solvents or a pure solvent, that should be continuously added at the top, and from the bottom with the help of a stopcock this goes down. While it passes through the column bed, it gets separated, and at the bottom of this column, if it is connected to some detector, so the detector can help how many components are passing through the column at what time, that is called elution time. So, this is the basic principle of column chromatography. That basic principle of column chromatography has been extended to high pressure liquid chromatography, because column chromatography technique is a time consuming process. For separation of one mixture, it may take few days, whereas the same can be done within an hour or even less, within a half an hour time or less than half an hour time in a high pressure liquid chromatography. Basically, a high pressure liquid chromatography instrument contains a column, short column like this. Its length might be say 1 feet or something like that, and it is connected to a high pressure pump through connected with a injection port. So, in that injection port the sample is injected, and that pumps takes the solvent from the reservoir and pumps through the injection port to the column. So, this way it carries the mixture through the column, and column contains a packed bed, and while it passes through the column, depending on the partition coefficient of the component between the mobile phase and the stationary phase, separation occurs, and from the other side of the column it comes out, which is connected to a detector. It may be refractive index detector or UV detector, that helps to know the separation, and it gives a picture like this. Say if there are more than one component, it may look like this. So, each component specified for one each peak specifies for one component, say component 1, component 2, component 3, component 4. This is the elution time, and this actually say intensity of the detector. So, this component 1, it gives a peak like this. This indicates this is proportional to the concentration, and this is the elution time of the component 1, elution time of the component 2, elution time of the component 3, component 4, like this. So, this way it shows that it is separated. Now, it cannot tell you exactly the identity of the component 1, 2, 3, 4 here. It just separates and indicates that the components in a mixture are separated. In order to know that, you have to collect the component or the solute present in this fraction. Then you have to collect means you have to isolate and then purify, or as well as you have to take the solid things, and then you have to go for spectroscopic analysis, IR, NMR, etc. From that you can know what is the identity of the fourth component. So, there various details are available in a book, you can go through that. Now, this concept has been extended to gel permeation chromatography. Basically, a gel permeation chromatography instrument contains a column which is packed with say porous beads of small particle size. That porous beads are made of cross-linked polystyrene. So, cross-linked polystyrene beads are used as a packing material in gel permeation chromatography. Basically, there is no difference between the principle between the GPC and HPLC, only the column packing material. GPC contains packing with spherical beads. Since it is porous, what happens if you inject a polymer solution of dilute concentration, small concentration, what happens? It enters the column. On entering the column, smaller molecules can enter into the porosity of the beads, pore volume of the beads, porous space of the beads, while bigger molecules cannot penetrate within the bead, but it passes through the interparticle space like this, it moves this way. So, depending on the size of the polymer molecules, few will enter into porous beads at a faster rate, medium sized can enter into the porous beads at a lower rates, whereas biggest molecules would not penetrate at all to the porous beads. So, while it comes through the other side of the column, then it is a separated one, that means fractionated one, that passes through a detector that detects that it contains so many different fractions, fraction 1, fraction 2, fraction 3, fraction 4, fraction 4, 5 like this. Now, if you have a calibration standard, say you have to take one polymer of standard molecular weight, known standard molecular weight. First, you have to run that GPC with the standard molecule, standard polymer of known molecular weight, plot a calibration curve, you will get a calibration curve. Based on that calibration curve, you can know the distribution nature of your test polymer solution, of which you want to measure the molecular weight. So, this is the basic thing what is done in gel permeation chromatography. In fact, majority of the molecular weights of majority of the polymers are verified or known or measured by this GPC, because all the time this absolute molecular determination techniques may not be accessible to each and everybody. Now, let us pass on to other part of the structure property correlations of polymer materials. Structure, I mean, you have to consider that a polymer molecule, it has a chemical structure. Say you think of a polyester, its chemical structure is known, polyethylene, its chemical structure is known, polypropylene, its structure is known. So, chemical nature as well as its configuration, these are known from the theory. Then, in order to predict the properties of a polymer sample, how this structure and configuration of polymer molecule helps. Not only that, you have seen that with the increase in molecular weight of polymers, their properties changes. Sometimes the properties level increases, or with the decrease in molecular size, properties decreases. Not only that, with the extent of branching with the extent of linearity, with the extent of non-linearity, with the extent of cross-linking, say cross-linking, less cross-linking density, low cross-link density polymer, high cross-link density polymer, there is a variation in properties. So, we have to know, and there is also variation in morphology of structure and morphology of the polymers. Now, this diagram shows interestingly, say this is temperature axis, melting temperature of polymers in degree Celsius, and actually there is a problem in the figure. This is 20, this is 24, read it, shifting of this thing, 0, 16, 20, 24. Now, there are 4, 1, 2, 3, 4, 5 curves. This is also a curve, this is a horizontal one, this is also a curve. This curve 4, this shows the Tm melting temperature of linear polyethylene. What is the x axis? It is the chain atoms in repeat unit, that means number of carbon atoms per repeat unit. Try to understand. You think of a polymer molecule, here the information is shows like this. In the polymer molecule, what are the number of carbon atoms in per repeat unit? Based on the carbon atoms per repeat unit, their melting temperatures varies, changes. Now, if you think of polyethylene, there is no change in melting temperature with the increase or decrease of number of carbon atoms. Whereas, in case of carb 1, which actually correspond to polyureas, carb 2 correspond to polyamides, nylons, carb 3 correspond to polyurethanes, and carb 5 correspond to polyesters. So, this is polyurea, this is polyamide, this is polyurethane, this is polyester, okay, say PET. Now, you see in this case, with the increase in number of carbon atom in the repeat unit, their melting transition decreases and approaches that of polyethylene. So, is the case with polyurethane, so is the case with polyester. In this case, in case of polyester, it also approaches that of polyethylene. That means, the spacing between the repeat your functional groups, if there is a change in spacing between the functional groups, then the melting temperature is affected. I give you a simple example. Say you consider this PET and PBT. What is PBT? PET, polyethylene terephthalate. That means, glycol is ethylene. There are 2 carbon atoms in the glycol part. Polybutylene terephthalate, there are 4 carbon atoms in the glycol part. So, there is a difference of 2 carbon atoms from PET to PBT. Obviously, the distance between 2 ester groups here say suppose this is case of PET, this is the distance, in between there is CH2 whole 2 and in case of PBT CH2 whole 4. So, obviously, the distance between these 2 carboxyl, sorry, I should have drawn little this side. So, this length is longer than this length. So, obviously, the melting temperature of PBT will be what? Okay. Because methylene group, this carbon chain, carbon carbon bond, it can rotate and it is flexible. it is highly interesting. Similarly, polyethylene, simply polyethylene, here is also it is flexible, but and this flexibility is related to its glass transition. I will discuss what is glass transition later. So, polyethylene is flexible and but its flexibility is little restricted due to closure packing of the linear chain molecules because of the size of the hydrogens attached to carbon. Now, you think of a polymer where one of the hydrogen in ethylene unit is replaced by one a phenyl ring, it becomes polystyrene, flexibility is lost. So, replacing one hydrogen in ethylene by one phenyl ring, its flexibility is lost. Here you have seen the chain contains methylene group as well as one phenyl ring in polyester. If you compare this polyethylene and this polyester, what happens? The melting point of this polyester PET is around 265 degree Celsius Tm of this polymer, whereas Tm of this polymer is, say if it is HDP, it is around 130 degree Celsius. Look at the difference between these two. Why so? It contains carbon chain, carbon carbon bond, it also contains carbon 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 bond. In addition to this carbon carbon bond, it contains one carbon oxygen bond, as well as in this molecule there is one phenyl ring in the backbone itself. Now, that phenyl ring in each repeat unit restricts its mobility. So, this becomes rigid at ambient condition as compared to this one, although this is rigid because of this your smaller size, but there are other polymers which is not that rigid. Again, if you compare this polymer with this polymer, it is rigid as well as it is brittle. It is a brittle polymer. This polystyrene is a brittle polymer, whereas polyethylene is a tough and strong polymer. It can absorb impact energy, whereas polystyrene cannot. So, these things should be understood or known by critical examination of the repeat unit formula and the repeat unit configuration. It is not very difficult, provided you know the molecular formula of the repeat unit, provided you know the bonding nature between the atoms in one repeat unit. Do you understand? Here is another representation. You see, melting temperature of polymers are related to number of side chain carbon atoms. Well, if we consider that the melting temperature can vary depending on the number of carbon atoms per repeat unit between two polar functional groups. But what can happen if there is a branch structure or a branch short or long branch attached to a backbone chain, and that too what are the number of carbon atoms present in that branch chain. You see here the melting temperature first increases if the number of carbons are less. Then with the increase in number of carbons in the branch, that means for long length of branch structure, the melting temperature decreases. Further, it shows an increasing trend. Why? After passing through certain length of the branch, if it goes beyond that, what happens? It behaves like a linear molecule. That means it can arrange in the alignment with the main backbone chain. So, it shows increasing trend of melting temperature beyond certain number. So, these are the things we will find. That means, you have to, if you want to correlate the properties, say thermal properties, mechanical properties, solubility properties and other properties, you want to find out the reason why it is so, then you have to look into the structure of the polymer. If it is an unknown polymer, then you have to evaluate the chemical structure of the polymer, then you have to correlate the properties. Look at the structure, these structures are available in books. What is the structure? It shows a formula, chemical formula representation of a cellulose molecule, which basically shows a repeated union of anhydroglucose units. These are actually anhydroglucose units. Okay. It contains both primary and secondary hydroxyl groups. Okay. Primary and secondary hydroxyl groups. You can see in other way also. This may be little complicated to students from non-chemistry background. Just you see, you can visualize in this fashion also. This is primary hydroxyl groups, these are secondary hydroxyl groups present in cellulose and hydroglucose ring. Okay. Now, these hydroxyl groups enter into extensive hydrogen bonding inter as well as intramolecular hydrogen bonding. What happens then? I told you cellulose is a thermoplastic polymer, but it behaves like thermoset polymer, because we do not find any solvent for cellulose. We cannot melt cellulose. If you heat cellulose, it will not melt, rather it decomposes. Why so? Because we know a thermoplastic polymer, if we put a thermoplastic polymer in a solvent, it goes into solution. If we heat it, it softens and melts. But cellulose, although it is a thermoplastic polymer, it does not, because it contains extensive inter as well as intramolecular hydrogen bonding. What are those things? So, suppose it contains OH, here also it contains OH. So, this O and H can enter into hydrogen bonding. So, there may be many, because a look into these units, each and every unit can enter into hydrogen bonding with other polymers. So, total amount of hydrogen bonding per gram mole of polymer is huge. So, it does not go into solution, but it can be converted into solution provided you carry out some chemical treatment. What is that? Suppose if we represent this cellulose as ROH, cellulose is basically an alcohol, chemically an alcohol. So, if we represent a cellulose as ROH, in order to make it soluble, you add carbon disulfide along with sodium hydroxide. What happens? It forms sodium cellulose xanthate. This is highly soluble in water. Now, you have read viscose rayon, cellophane, etc. These are nothing but regenerated cellulose. How it is done? How this regeneration is done? What is the viscose process? What we do? We take sodium hydroxide solution, alkali solution. Into that alkali solution we put cotton, then we add slowly sodium hydroxide carbon disulfide CS2. So, that is highly reactive and forms this kind of compound. Then when it is put into an acid bath, say dilute sulfuric acid, what happens? You get the cellulose back. This is regenerated cellulose. Mercerized cotton, processed cotton. Today we are using this processed cotton as our garments. These processed cottons are soft, whereas raw cotton is very rough. Roughness of raw cotton is decreased by this viscose process, mercerization process. Cellophane is nothing but regenerated cellulose film. How this cellophane is made? Joris and many other products are obtained from wood pulp. There is an industry in Bengal they are making in huge quantity this rayon and other regenerated cellulose etc. from wood pulp. You will be surprised to see. So, cellulose is extracted from there by pulping, isolated by pulping, then it is interacted with carbon disulfide. There are various other techniques, say cuproammonium technique other than this viscose process is also available. So, if you are interested you can go through there. Now, what I wanted to say with this representation, there is extensive hydrogen bonding. What happens here in this reaction? Actually, this breaks these hydrogen bonds. Once it breaks the hydrogen bond, then the cellulose go into solution. Then when it is passed through acid bath, the cellulose is regenerated. Now, once the cellulose is regenerated, what happens? It cannot reform the same number of hydrogen bonds as it was present originally, and by virtue of this large number of hydrogen bonds present in this molecule, intermolecular hydrogen bonds, this cellulose is crystalline, highly crystalline polymer. Now, its crystallinity is reduced by this viscose process, mercerization process. You can verify it. You take the XRD of raw cotton, then you take the X-ray diffraction of this mercerized cotton, you will find that its crystallinity is reduced. That is due to decrease in hydrogen bond. Also, you can verify this with the help of Fourier transform infrared spectroscopy. There you will find that hydrogen bond has been decreased, extent of or concentration of hydrogen bonding has been decreased after this viscose treatment. Here is another example of a polymer, say polyamide, nylons or polypeptides. In polyamides, the helical structure in polypeptides, in proteins, the structure is solely dependent on this hydrogen bonding as well as cross linking. Their cross linking atom might be sulfur and or other things, other atoms in proteins. In polyamides, the strength of polyamide is dependent on the high polar interaction arising out of this interaction between oxygen and nitrogen present in separate different molecules. So, these also forms strong intramolecular hydrogen bonds. Okay. So, these intramolecular hydrogen bonds actually control its solubility in a solvent, control its melting temperature. Now, at this point I should mention that these polyesters and polyamides are manufactured or synthesized in melt condensation process, not through solution process. It is not possible. Of course, there is a technique known as interfacial polymerization technique, which can be utilized for synthesis of nylon like polymers other than melt polycondensation. And this melt polycondensation, what happens? Once these molecules grow in size, then their viscosity gets very high and it melts at higher and higher temperature. That is why you have to maintain a very high temperature, say from 260 to 280 or 90 degree Celsius temperature in the reactor, so that it remains fluid and you can get high molecular weight nylons. So, here you see also the effect of hydrogen bonding on the molecular polymer properties, their melting temperature. The melting temperature is not all. This hydrogen bonding make them crystalline, make these polymers stiff, make these polymers strong. Now, this nylon is so strong, provided the length between two polar and functional groups, amide groups, length between the functional amide groups, if that is regulated, then one can get very tough and strong polymer, which is used for making mechanical gears. Mechanical gears are made of this nylon, self lubricating gears. Self lubricating gears are made from these polyamides. Today, sometimes self lubricating gears are also made from ultra high molecular weight polyethylene. Now, here you understand where from this strength comes, where from this your toughness comes. In case you just compare this nylon, ultra high molecular weight polyethylene, polycarbonate and aromatic polyamides, polyether ether ketones, polysulfones. These are engineering polymers, polysulfones, polyether ether ketones. Please note down engineering polymers, polyether ether ketones, polysulfones, aromatic polyamides, polycarbonates. These polymers are known as engineering polymers, and these polymers can withstand higher temperature, or their service temperatures can be very high, as well as they can bear huge mechanical load without breaking. That means, these polymers are also mechanically tough. Not only that, the dynamic properties I mean device exposed to dynamic stressing or dynamic loading, it does not fail. That means, it can absorb this cyclic stress energy without fail. So, this diagram, this picture shows an indication how that is done. Now, here you see, if it is made of aliphatic chain, if the units present between two polar units an aliphatic chain, what happens? Aliphatic chain is flexible. So, you can get flexible structure. Now, if you want to have a rigid structure, then you can place one phenyl ring here. You can have a polymer exclusively made of aliphatic chains along the backbone, aliphatic units, or you can have exclusively aromatic units, or you can have a mixture. That means, you have the tailorability option. You can design a polymer, you can synthesize a polymer having both aliphatic as well as aromatic units in one backbone chain, as you like, you can make. So, this indicates a concept, say you are having a polymer chain exclusively linear made of aliphatic. Aliphatic linear polymer. Now, along with these aliphatic units, if you have some aromatic rings placed after certain intervals in the length, then their property changes, flexibility, that means this is mechanically stronger than this polymer. This polymer is thermally more stable than this polymer. So, what we have got? Improved mechanical properties or higher mechanical properties, higher thermal properties. But at the same time, if we move like this, we can achieve a polymer with high brittleness. So, you have to think of the impact properties also, you have to keep in mind the impact characteristic also. We need a strong polymer as well as high impact polymer, as well as thermally stable polymer, as well as we must see that it becomes easily processable. That means, you have to think of the processability temperature at which it melts. Not only that, if we go for solution processing, we have to find a suitable solvent, so that this polymer goes into solution easily. But as you move from this linear structure to this kind of structure containing phenyl ring, then we have to compromise with solubility, we have to compromise with the mechanical properties, etc. This way you have to optimize if you want to tailor the structure. Now, what happens? This way we can just lead to a structure like this. This is a single strand polymer. This is a combination of single and double strand polymer. This is a double strand polymer. We can have polymer like this. We can have polymer like this. So on. What are the characteristics of such polymers? This is soft flexible, this is rigid polymer, rigidity is increased. This is far rigid polymer, again here the rigidity and thermal stability they are compromised here. These polymers are known as multi-strand polymer or double strand polymer, or known as ladder structure, ladder polymer. This looks like a ladder, looks like a ladder polymer. They are thermally stable. Why? Now, if there is some agency which can break this point, still polymer remains stable. The polymer is not disintegrated, because the polymer chain integrity is held through this. Like this, the polymer structure is not totally destroyed. So, this is a thermally stable polymer, but at the cost of solubility, at the cost of processability. These polymers are difficult to process. One example I give you, that is Kevlar, used for making bulletproof jacket. Is a product of DuPont. What is Kevlar? This is aromatic polyamide. Made of, who can say? Kevlar aromatic polyamide. Who can say? Karthikeyan? Why not? I told you in the class. Phenylenediamine and terephthalic acid, aromatic polyamide, Kevlar, not iso. If you take isothalic acid, the polymer will be different. It gives the highest melting point, melting transition in that series. So, you can take terephthalic acid, isothalic acid and metathalic acid, meta structure, that means here you see in the para position, if it is connected in the meta position, then the molecular symmetry is lost there, and that using this metathalic acid you will get Nomex. It can give you a aromatic polyamide film, and this gives you Kevlar fiber. You write down the structure using metathalic acid in the meta position here. Okay. Also, you can have a para substitution, paraphenylenediamine. You can take metaphenylenediamine. Okay. So, this way you can have, all are aromatic polyamides, but by virtue of this your isomerization, you are getting different melting transitions, different mechanical properties. Now, this kind of, this is one polymer, and you can have polyamides, these are polyamide, you can have polyamides. I have shown in the earlier slide, I have shown here you see this is a polyamide, it is a polyamide. Now, these are not so easily processable, you cannot melt it. So, melt processing is not possible. When this kind of polyamide were developed, it was abandoned due to its lack of processability, but scientists could develop its processability by through the route of polyamic acid. Now, this amide ring, once it is formed, then it is difficult to further process. So, what happens? They took the same reagents, they got a precursor polymer, pre-polymer of polyamic acid by reacting this, actually this is BTDA part, benzophenone tetracarboxylic dianhydride, sorry PMDA, I am sorry, this is PMDA. Pyromellitic dianhydride. So, one can take pyromellitic dianhydride or benzophenone tetracarboxylic dianhydride. So, these can be used for making high temperature resistant polymers, and their processability is difficult. If you want to make polyamides, then you have to go through polyamic acid route. Further, humidification of this polyamic acid leads to polyamide. Details you will get. We refer to this book. There are so details, so many things are there, itself will become a course. So, only here I can indicate for your information, those who are interested you can take. What is this polymer? You can say not showing. This is actually, you are not getting in the screen. This is polyacrylonitrile. Actually, polyacrylonitrile also enter into intermolecular hydrogen bonding. Nitrogen is there, so that nitrogen enter into hydrogen bonding, although not that so strongly as you have seen in case of polyamide. That is why polyacrylonitrile PAN polymer, it is a ordinary polymer. This is used for making artificial wool, polyacrylonitrile. This also, this PAN is also used as a precursor polymer for carbon fiber or graphite fiber. The solvent for PAN is sodium thiocyanate NaSCN, in which it is highly dissolved aqueous solution, aqueous sodium thiocyanate solution. There is one industry in Haldia, CFCL, Consolidated Fibers and Chemicals Limited. They manufacture this PAN fiber, artificial wool. Acrylan, synthetic wool is known as what is it called in the market? In the market we get it by in the name of, what is that called? Acrylic fiber, these are PAN fibers, acrylic fibers are PAN fibers. So, that in this PAN fiber, we find there is extensive hydrogen bonding between this nitrogen and hydrogen. Is it coming to the screen? There is some problem. So, this is